Okay, so let me just introduce Cyril. So Cyril is a senior researcher at Microsoft Research NYC. He works on theory and algorithms for prediction and decision-making in dynamical systems, large-scale learning and language modeling. He completed his PhD in computer science from Princeton under the supervision of Professor Ella Hazan. He was also a student researcher at Google AI. Before that, he worked on Laplacian solvers and exoplanets at Yale. So we are very happy to have you here, and we are excited to learn from you.
All right. Yeah, thanks so much for the introduction, and thanks for inviting me here again. It's always fun just to talk about some stories from the trenches of training deep neural networks, maybe as someone who'd like to devise theory and make some kind of understanding amid all this chaos going on these days. So I'm excited to present a few stories about how we at MSR and with various collaborators around academia and beyond are trying to figure out this kind of story of bridging the theory practice gap in deep learning, maybe slice by slice. Okay, so I'll kind of go through a very quick perfunctory framing slide just for some current thoughts. Maybe they'll be kind of redundant or tautological. We're just going to use these to help us frame what we're going to be talking about. So I guess my personal view on deep learning, as it will kind of last beyond the fads and trends of like the next decade, and maybe just be used as some mainstream scientific tool in like the far future when we have different hardware, different architectures, different kind of problems we want to solve. Probably what I view to be kind of eternal in deep learning, or kind of the lasting lesson in this era of deep learning, is that we have this sort of free lunch of feature extraction via differentiable circuits trained end to end, like SGD on an ImageNet classification loss on some AlexNet classifier, and furthermore, in recent years, I guess we've really been able to make transduction between forms of data very useful. Right. So maybe just to give some illustrative example that maybe dispels some like 5-year-old myths about deep learning. We have these like UNet architectures. These are like by now very mainstream. I think ArcGIS provides this as some kind of primitive that you can just call in the Python library. We have these neural architectures that are quite sample efficient and can translate between modalities of data in some like way that immediately automates lots of previously cognitively like annoying and taxing tasks, such as like the sort of dense annotation of satellite images. So this is kind of what's exciting to me about like the applicability of deep learning these days. We're really in the middle of an era of having our imaginations like extended from kind of the lab to various deployments across the natural sciences and industry. And I guess from the viewpoint of someone who likes to think about theoretical problems, maybe the way I contextualize the empirical successes of deep learning is that like we've spent a lot of time throwing other ideas at the wall. And it seems that in some modalities, in particular, when you kind of very heavily suffer from a curse of dimensionality operating on the raw inputs, such as the pixels in some megapixel image, deep learning, this sort of generic technique of differentiable kind of end-to-end search, giving us indirectly useful features, just seems to lie in some sweet spot where we can run these things on kind of modern hardware on like with data sets that we could hope to collect. And like somehow I view this maybe not to be such a sad story of deep learning causing the sort of obviation of swaths of theory, but really it's a kind of new horizon for the sort of challenging modalities of data we're newly able to tackle. So Okay, I guess I won't ramble on too much longer. The role of theory I view in this space is to provide a number of things. I think like inspiring interesting algorithms is maybe my personal favorite, and it's the mode of research I've kind of gravitated towards. I guess the challenge as someone who likes thinking about theoretical abstractions in this space is it turns out that you know your um, your selections of hyperparameters or algorithm configurations tend to have lots of rippling side effects. When you kind of change the learning rate or the momentum or the weight decay in some deep learning setup, and you start chugging this like training pipeline, everything seems to have entangled side effects, and so like empirically, it's rather hard to understand, especially if we kind of insist on existing within some like if we're kind of tied to some abstraction of how these networks train. I guess what I'm striving to do in this space, in whatever ways I can, I guess I've put kind of the word towards in the corner of the title slide, and this is just some caveat that we're far from completing any picture of this, is that I'd like to like derive like useful understandings of the dynamics of learning as they occur in these state-of-the-art pipelines, and like kind of gravitating towards algorithmic consequences here. So in this talk, we'll talk about just some quick vignettes on like the sorts of things you can do like in the near term around kind of state-of-the-art deep learning settings. Okay. Oh, this is not advancing. Okay, just very quickly, I guess where we run into a sort of problem with applying classical theory in these sorts of settings is that maybe we can view kind of theoretical CS and statistics and optimization and such for providing some tools for reasoning about the way algorithms behave under uncertainty. And just to give some like broad cartoon of the sort of roadmap in this space, on one hand we have convex optimization, where we have provable guarantees, say minimax convergence rate guarantees in like certain settings, and on some extreme end, we have complexity results, equally provable. We can quantify the hardness of instances and like which kinds of problems we cannot hope to solve. And maybe the trouble is that life exists in the middle between tractable and intractable, and there are various kind of positive results out there, and maybe like a lot of the theory that we work on in this space is trying to advance that which we can provably analyze in this space. And it really just seems like deep learning is in between, right? There's always a harder question theoretically we can ask about characterizing the precise behavior, even of a two-layer neural network. And of course, like it's kind of especially challenging these days as deep learning provides such quickly moving and numerous moving targets. To actually produce theory with useful algorithmic consequences in the near term. I guess in the long term, there are lots of things we can pursue as researchers, but for maybe pushing some state-of-the-art, like near-term technological advancements, maybe we have to actually feel somewhat accountable for seeing what's actually going on in practice at a rather granular, inconveniently kind of annoying level. I guess my kind of bird's eye view of this is that there are various idealizations that we devise to analyze deep learning, and the theory practice gap sort of arises generically from the failure of let's say, like a state-of-the-art language model to exactly conform to these idealizations. So in this talk, I'll talk about some slices of theory and basic empirical research where I guess I personally have kind of run some state-of-the-art-ish experiments that kind of indicate that we can make some near-term progress in this space. Okay, so the agenda broadly, we're going to talk about learning rate schedules. I'm going to argue that investigating this fundamental convex setting with, let's say, stochastic or noisy gradients is a really nice, beautiful tractable slice of the generic kind of theory of large-scale optimization, and we're going to just investigate this one small slice of optimization. We're going to talk about learning rate schedules, and we're going to see that they can take multiple roles. Like if you select a learning rate schedule, this is this actually very high dimensional hyperparameter, and maybe you specify this global trajectory of update sizes. It's going to have multiple side effects and consequences that we can characterize. This is some minimal setting in which we already have like many complex factors to trade off. And then we're going to investigate what this kind of implies for actual deep learning setups. And this is joint work with Naman and Serbi. We're going to switch gears after that, just to briefly mention this kind of class of very weird experiments, which came from this nagging question, like what the heck are adaptive gradient methods doing on state-of-the-art neural architectures? So we're going to talk about some history, sort of unnatural looking, especially if you're kind of coming from a theoretical direction, state-of-the-art experiment. And maybe the point I'll try to argue here is that we should take a rather inclusive, maybe pessimistic view of the abstractions that are appropriate for kind of understanding everything in a deep learning pipeline. But we can actually design experiments. We shouldn't just flail around. We can actually discover some new empirics to kind of zero in on the phenomenon of deep learning. And this is with some more collaborators, Naman, Rohan, Ilad, my advisor, and Tomer. And finally, I'll just spend a couple of slides just giving a little teaser for our latest work of these three on trying to derive a little bit of theory, make some theoretical headway, at least as to what the statistics of a transformer or attention model are. There's this like very open-ended, maybe multidisciplinary question of like, what is going on as transformers are seem to be achieving reasoning or intelligence, general intelligence like behaviors in multiple modalities of data. So I guess in here, we'll just briefly talk about how we have some statistical story for what's going on. We have some mechanism by which transformers are picking out circuits in a sort of attribute efficient way. And we'll kind of leave some interesting open questions arising again from some empirics where we train actual transformers on some interestingly designed tasks. And this is a collaboration with Ben, Serbi, and Sham. Okay, so let's hop into learning rate schedules. Just very quickly, we're going to talk about this setting of stochastic first order optimization. We're simply trying to minimize a function with d parameters. Think of this as the neural net training loss with some noisy oracle. You can think of this as a stochastic oracle. We won't actually need any of the details of stochastic optimization here. Of course, the workhorse algorithm. We're just kind of making broad claims as to what is actually being run on these like large neural architectures in practice. The kind of fundamental algorithm maybe will run when we have a gradient oracle as this sort of local search in the direction kind of given by that oracle iteratively, right? This is just vanilla stochastic gradient descent. And there's this basic question of how do you select the learning rate schedule? All right, so if you know that you're going to train for some number of iterations, or if it's an indeterminate number of iterations, what should your update step size be? And this sounds like a simple innocuous question for which maybe in some kind of views of the world, or some theoretical idealizations, like like the answer to this question is very obvious. But I guess ignoring like which theoretical angle that we're going to take, there is this question of a trade-off of kind of convergence speed versus stability. and like we'll directly tackle that using one theoretical lens. So I guess even empirically, like the answer to this question is not obvious, and we'll do a little review of the theory and empirics around this this simple question. All right, so I guess tackling this from the optimization angle, we have like a certain recipe for doing analyses that have given us various interesting results, which is, well, first we're going to come up with some idealized assumptions on what the function is and maybe what the structure of this gradient oracle is. Maybe we'll say like there's some like these gradient oracles are IID random variables with expectation equal to the gradient with variance bounded by some sigma squared, right? So when we have these assumptions, maybe at first various additional assumptions on top of f being a convex function, we can derive minimax convergence rates, right? We can say under worst case instances of f in some function class of interest and some assumptions on the stochastic gradient oracle, we can get these sorts of, we can quantify the convergence rates of like this optimization trajectory towards the minimizer. I guess towards bridging things from the theoretical angle towards what's actually going on in modern large-scale learning, like from linear regression to your GPT-3, there are various theoretical refinements of this classical theory where maybe we'll put on some additional assumptions and find that the right choice of learning rate is some kind of like a polynomial or exponential or stepwise decay. And of course, lots of kind of surprising kind of discourse between theory and practice happens here, such as this recent work by Zhang and Sanjeev Arora showing that you might want an exponentially increasing learning rate in the presence of like interactions between batch norm and weight decay, right? So suggest reading that paper. That's a lot of fun. I guess like there is such a rich like theoretical toolbox for designing the learning rate schedule, yet in practice there's such a huge gap, right? So like I guess I sort of view this as a gap between the assumptions on F and like this stochastic oracle under which you're proving minimax guarantees, and the specific instances that you would like to actually run your optimization algorithms on. Right? And I guess there are many kind of levels of granularity at which to view neural net training, and maybe the ones that practitioners are using to actually train their neural networks, carry many side effects that are kind of discarded or improperly characterized by theoretical idealizations. So I guess in practice, just in talking to people who train state-of-the-art neural networks, you'll find that they're not using these 1/t or 1/t learning rate schedules. They're certainly not measuring the gradient variance or measuring the sort of initial distance from the optimum or the error tolerance that they would like to have. And what you really see in practice is this preponderance of heuristics, right? You have these polynomial annealing schedules, you have constant schedules, you have all these stepwise decay schedules that you see kind of earlier. Maybe in some ways they're doing what the theory from the previous slide predicts, in some ways maybe not. And then you have these exotic schedules that people just design, they work, and this is just a sequence of numbers. You'd think that everyone could agree on a sequence of numbers, but they can't, right? People propose this cosine learning rate decay. Looks very spooky, and it just seems that the test of time of millions of researchers and engineers training neural networks has decided that this cosine decay is in the canon of things which work well out of the box. So I guess in personally training some of these large models, I am very personally frustrated by the learning rate schedule, and we run into this effect, this empirical, horrible fact that your decisions about the learning rate schedule modulate so many things, and they are like intertwined with the batch size, with the architecture, with the data set, with the like optimizer. So this is really a situation where maybe there'll be a sim to real gap between theory and actually training a model. Okay, so in this work, we're going to present a very specific learning rate schedule. And that is something that is in this old paper that we actually translated from Russian. We thought we had derived some of this ourselves, and then we kind of searched for this and found that like the old Soviet like PDE literature actually constructed this way ahead of its time. So we call this the fractal Chebyshev schedule. I'm just first going to define it before we analyze it. So, agnostic of any theory that we might apply, this schedule is defined by this sort of reciprocal cosine function. You can sort of visualize this as like taking a semicircular arc along the real line and dropping equally spaced points down to the horizontal axis, taking the reciprocals of the sort of positions along that axis, and then permuting these in this recursive order. And this recursive order is kind of defined by like one kind of doubling of this recursive permutation involves like taking the permutation, a copy of it, reversing it, and then interlacing these interlacing the indices and repeating this as many times as you like. So I guess our theoretical findings are that when f, in the idealized setting of convex and quadratic f, we actually show that this gives Nesterov-like acceleration without the kind of conventional tool that people associate algorithmically with accelerated convergence in convex optimization, which is this class of momentum methods. And the new contribution on top of this this old work is a stronger stability guarantee for the entire trajectory. I guess these authors in 1971 were motivated maybe by high dimensional least squares problems under numerical error. Under other forms of error, maybe it was more natural to consider a stronger stability guarantee. So maybe that accounts for why these authors who invented this amazing schedule did not exactly derive our result. And certainly something that could not be run in 1971 is deep learning. So we find that this schedule can actually train neural nets at surprisingly large learning rates. Okay, let's hop into the theory. Okay, so as I said, the main result is going to be this sort of acceleration plus stability. So we'll give a mini lesson in one slide that just builds up to this result. Okay, so we're going to consider this idealized setting that is maybe the simplest setting in which we have to make algorithmic choices that account for curvature of the optimization landscape. Right, and that is this convex quadratic with some minimum shallowest curvature, given by lambda min, and the steepest curvature given by lambda max. And we will define this condition number, as a standard in this literature as the ratio between the steepest and the shallowest curvature directions. Right, and this is some setting even in the absence of the stochastic component or the noisy component. This is some setting of interest that where the kind of algorithm design objective is maybe to is to bounce around the kind of steepest walls of this landscape in a way that reaches the minimum the fastest. Okay, so we're going to run gradient descent with the learning rate schedule and some noisy oracle here, just as was true when we introduced this problem of scheduling the learning rate. And of course, classical theory, or maybe basic theory, gives us an optimal learning rate choice, an optimal constant learning rate choice, when we're sort of dominated, like when the convergence rate is dominated by the curvature rather than the deviations in this gradient estimator. And this is really to be interpreted as the largest stable step size, right? It's going to scale inversely with the kind of curvature in the steepest direction. And this is so that your steps are as large as you can take without overshooting in the in the directions of the steepest curvature. Okay, and I guess it's a sort of classic analysis that in this strongly convex case, like this algorithm with the constant learning rate will will converge at this. I guess some people call it linear rate, some people call it exponential, like towards the minimizer, and with very routine analysis, you can show that this is stable with a certain constant depending on this curvature with respect to perturbations in the gradient estimator. Okay, so our main theorem here is that if you're allowed to vary this schedule with time, we get this accelerated convergence rate, right? This is something that you usually see in the kind of in the classic analyses of Polyak momentum or Nesterov momentum. That there's an accelerated gradient descent kind of convergence rate with respect to the curvature, and this this stability that is just polynomially larger than that of this stable constant learning rate gradient descent algorithm, right? And I guess the thing that really surprised and delighted us was that this schedule contains a lot of steps that are above this largest stable threshold, and somehow this schedule is still stable. And I guess the cute thing is that, well, one, you cannot get this sort of acceleration even with like a greedy adaptive algorithm that that takes the best, that takes the step size that makes the most local progress possible. This is a sort of classic result. So this learning rate schedule is provably making negative progress locally on the objective. And stability-wise, I guess this fractal permutation ends up being necessary, where if you take these steps in the wrong permutation, maybe you'll still get acceleration, but like the sort of baseline that we're comparing with is taking these large unstable steps will actually blow your iterates up exponentially. So I guess this is just a bit of context for why it's such a surprising result mathematically. Okay, so to make a quick path towards just deriving this kind of result, we can go through some old history by now. And I guess in the back in the old days, when people were not training deep neural networks, but had these largely squares problems that they wanted to solve by these methods of relaxations, which in these days we'll just call gradient descent, it was found that there is this connection between learning rate schedules and polynomials, again, in today's language. Right, and the way we can actually just go through the entire proof, it's pretty transparent. For a convex quadratic function, or just for any quadratic function, of course, the derivative of a quadratic function is a linear function. So that gradient descent actually applies this sort of linear operator that depends on the kind of curvature matrix of the function, as well as the learning rate, to your current residual, okay? So in this sort of quadratic noiseless case, just in summary, gradient descent with a learning rate is a dynamical system, and you control this like scalar input, which is the like learning rate at each iteration. And then you can just unroll this recursion, and you can sort of easily see that that the selection of learning rates in this idealized case corresponds to building up a degree number of time steps polynomial, and I guess various papers studying this have called this the residual polynomial. And so we've kind of reduced this optimization problem by viewing this dynamical system, as I guess like by viewing this as some kind of this entire process as some kind of control problem instance, as well, we'd like to converge quickly. That means we'd like to pick these etas so that this process like results in a polynomial that shrinks the residual as much as possible. And it was noted in the 50s that beyond the sort of polynomial implied by the like constant learning rate, there exists kind of polynomials that give a quadratic speed up. A canonical derivation is via the Chebyshev polynomial sequence. And I guess just to, if you want to actively kind of engage with this line of research a little more, there's a great blog post that that my colleague at Google Brain Montreal, Fabien, has published covering much of this. Okay, so this is the noiseless setting where optimization for least squares really is kind of this polynomial optimization problem. With like numerical error incorporated into this, which is what was considered by this paper from 1971, you, in addition to being responsible for choosing a polynomial that shrinks these residuals, you have some other constraints on this polynomial. Namely, if you need to pick these step sizes in some order, such that the partial polynomials you get out of kind of plucking the roots out under that sequence all remain small, right? And it's not clear that such a polynomial should exist. And you can kind of see this just by propagating a perturbation through this dynamical system. And just noting that in addition to this residual polynomial that we had earlier, the dynamical system also amplifies the effects of these perturbations, and can see that to get stability with respect to these perturbations, we need to at least make sure that these infix polynomials, which we get from kind of taking subsequences of the roots kind of implied by the learning rate schedule, like we need all of these infix polynomials to not blow up the effects of the perturbations. Okay, so now just to, this should give some hint as to the anatomy of our main theoretical result. Just pulling up the main theorem again. Of course, this convergence rate is classic. It was known in the 50s, maybe even the 1850s, that we get this quadratic acceleration out of uniform norm bounds on Chebyshev polynomials, right? And we get the stability constant, which is kind of our new result for this sort of every iterate analysis, by showing that under this fractal permutation of step sizes, like all of this, like all of these polynomials have kind of small uniform norm. And furthermore, even taking a summation over these uniform norms as this sort of error propagation requires, even this is sub-exponentially bounded. And I guess just going back to what the consequences of this are kind of conceptually, we note that we're taking many steps that are far above this horizon of stability according to the steepest sort of walls of this quadratic landscape. Right? So just pictorially, like the schedule consists of like roughly half of its steps lie in this like region of stability. And then the other half are actually gigantic steps, which might overshoot by a factor of condition number, right? Like think of condition number as this like anisotropy ratio that like governs your convergence rate in the first place. So like this algorithm is telling you maybe to take like step sizes 500 times larger than the largest stable one. And maybe the beautiful thing about it that like elucidates like what's going on conceptually with this fractal schedule is, well, if your Chebyshev polynomial is telling you to take some sequence of steps, not telling you like which order you should take them in, maybe you should take your largest step on your first iteration, your second largest step kind of halfway through, your third and fourth largest steps at the quarter points, and then so on. And so really we're overshooting, but like in the landscape, by this factor of condition number. And we're gonna nullify the effects of this overshooting using fractal copies of the fractal schedule, which themselves overshoot, which themselves are corrected by fractal schedules, right? And this sort of, you can imagine there's some kind of divide and conquer analysis that actually is what you need to prove these uniform norm bounds on the infix polynomials. Okay, of course, this isn't really a proof. You can look at the paper to see the horrible things that are going on to obtain a proof. We have these very funky trig identities and like a sort of combinatorial exchange lemma at some point. So I guess I'm hiding many, many details here. And I guess more things in the paper where we derive some more variants that were not necessarily considered in kind of numerical PDE land. Okay. So I guess at this point we're itching to run this on a neural network, right? So let's talk about that. So indeed, so I guess just as Polyak acceleration or Polyak momentum was maybe originally motivated by acceleration on some like quadratic in some quadratic settings, but maybe we'll run these on other problem instances such as other convex problems or neural networks. You know, we can just try out this acceleration, this sort of self-stabilizing learning rate schedule, hoping maybe that you know, if the kind of the higher order terms that distinguish like the kind of the real optimization instance from the idealized quadratic one, if these are kind of small enough and the perturbations are small enough, this might actually work. And lo and behold, it does. And this is a sort of nexus of open questions that we're still thinking about. And if anyone has any ideas here, they're very welcome. I'd love to discuss these things. Well, it seems that in practice, let's say for logistic regression on the MNIST dataset, this fractal schedule you know, can sort of pretend that the landscape, which is some general convex function, is quadratic, and we see some Nesterov-like speedups in practice. And yeah, we can train neural nets. You know, in this particular paper, we're not doing anything extremely state-of-the-art, but I guess in neural net training, like a very common way to select your learning rate is to pick the largest constant learning rate, or you know, the largest multiplier on top of some optimizer that specifies its own learning rate schedule, like the largest constant multiplier that causes training not to blow up. Right, that's a very common practice. As like an empiricist, just take the largest stable learning rate, and indeed, like even in practice, this lets us exceed instantaneously, making some negative progress, like the largest constant learning rate that that a neural net can handle. So suggesting that this idealization, you know, maybe we aren't interested ultimately in like in fitting a least squares model, but really we probably could not have arrived at this self-stabilizing schedule via any other analysis. And I guess there are kind of other experiments in the paper showing that, you know, even random permutations of like of this learning rate schedule, not specifying the permutation, failed to stabilize training. So you know, something maybe akin to what we're analyzing is actually going on to first order or second order, since it's quadratic. Right. So now connecting this to, I guess, the neural net literature. Like this may give some new foundations for like this sort of niche topic that you know, bubbles up every few years of superconvergence using special learning rate schedules, where indeed people consider the sort of microstructure of the learning rate schedule, and in particular kind of oscillating learning rates. So we're giving some acceleration viewpoint of that. And I guess the overall thing that made me very happy about this result is that just by looking at this convex setting that captures enough of the challenges, at least conceptually, of training a large model in the sort of curvature bottlenecked regime, you know, we're able to derive interesting algorithmic surprises beyond momentum. And there are lots of open theoretical questions here, as I mentioned. Just we don't know what's going on beyond kind of even quadratic convex functions. And there's of course some other question as a theoretical computer scientist of whether there are lower bounds or there are better schedules even in the same setting. Okay, so I'll pause here for any questions. This is, I guess, the main technical component of the talk, and then I'll walk through some post-entree desserts.
Yes, I have one question. For this fractal learning rate, let's suppose we were to take like a rolling average of it. Does the like mean expected value decay throughout the schedule?
That's a great question. So we have some, I really liked this analysis, but there was no place for it other than the appendix, where we show that the average learning rate is around root kappa times the like largest stable learning rate. So I guess it recall that the largest one is kappa times. As for taking kind of rolling window averages, yeah, like we should expect root kappa as well, right?
So it like never slows down. It's always going at like the same speed.
Right. And actually we get the same convergence guarantee roughly, like up to some polynomial factors for the forward or the reverse learning rate schedule. So certainly like for the purposes of like the theory that we're doing, it doesn't distinguish between the forward or reverse schedule.
Got
and
it.
we can kind of go back to the picture here. Yeah. I guess if you reverse this, there's still a very large learning rate halfway through.
Yeah, well, I wasn't sure if like those large learning rates were supposed to be decaying continuously, or if like it'll keep revisiting the same ones.
Right. So I guess just very formally, they'll decay as this sort of 1 over lambda min plus some like cosine quantity, right? Like you can sort of stare at these learning rates in this order to quantify the rate of decay. Great question.
Let's see.
All right. So I guess I can just move on to the next two parts somewhat quickly. Rambled a little. Yeah. So as I mentioned at the beginning, second part of this agenda maybe complements this work a little bit from an extreme other kind of very pessimistic perspective. So now we're going to talk about this other tool that is definitely a cornerstone of how people train neural networks. We're going to talk about vanilla SGD with this new add-on, an adaptive preconditioner. Right, so this is this matrix, usually a diagonal matrix that you hit the gradients with to determine the update. And I guess you can just sort of stare at this definition or the text, whatever you prefer. But this preconditioner is defined sort of adaptively, of course, by accumulating the squared values you see like throughout the training trajectory at the like of the historical gradients, and then normalizing the updates by this sort of root mean squared, or actually root sum of square, like statistic of these historical gradients. And I guess a sort of basic empirical question is, you know, after all these years, why has this heuristic turned out to be so eternally prevalent and robust? Again, like maybe ignoring any theoretical lens for now, and indeed for the rest of this section of the talk, just by looking at how many people in their various applied domains end up using Adam as their sort of bread and butter heuristic adaptive optimizer, we cannot deny that it would probably pay off to understand this. So I was kind of hooked on this question during my PhD, and there was a very frustrating plurality of answers in a sense, right? There's this single object, you know, this single algorithm, this change to this, like this innocuous change, maybe not so innocuous, to this local update defined by, you know, stochastic gradient descent. And I sort of found that there are so many perspectives on this. I guess the origins of these methods came from my advisor and friends from the online learning days, where this made total sense when you're in the regime totally dominated by stochastic or perhaps adversarial like perturbations to the gradients, like maybe in online linear optimization, like the Adagrad preconditioner like optimally adapts to the shape of the like gradient noise. I guess in a somewhat parallel way, I guess that's history is a little nonlinear here. The deep learning people came up with very similar rules, and I think I guess this is before the time I was in research, but my understanding is that there were sort of other intuitions coming from maybe just receiving the stream of gradients and wanting to get some lagged statistic, by kind of aggregating over many noisy observations of this like hidden gradient quantity that you'd actually like to track. And of course, like lots of other papers have come up, proposing kind of other related or perhaps unrelated perspectives on why these things work. There are perspectives on like automatically tuning learning rates to kind of curvature steepness. There are characterizations of these things escaping saddle points, or sort of clipping the heavy tails in the data. And of course, my favorite, there are these rebellious papers that actually show in some idealized settings that these methods can overfit or they can fail to converge, right? But I suppose that still doesn't change the fact that practitioners run these things and get these useful architectures to train. So this was a little frustrating. So I guess towards the end of my PhD, we were thinking about this experiment where we sought to simplify the space of these adaptive gradient methods rather than maybe proposing yet more optimizers. We considered this experiment, and I'll motivate it later. I'll just first describe the experiment of choosing two optimizers, such as like SGD and EDM. And we're going to do this funny binary operation on these optimizers. We're just going to view them as state machines, ask them for the updates that they propose, and then merge these updates so that you steal the magnitude from optimizer M and the direction from optimizer D. Okay. And you can kind of stare at these equations just to kind of see, we're going to normalize D's updates so we forget the magnitude that D took, and then we're going to measure the magnitude of M step, and we're going to have this like Frankensteinian step that we actually use to update the model, again on a deep neural network. I guess there's kind of one remaining degree of freedom, which is like in what partition of the neural net's trainable parameters do you do this on? And I guess I won't go into too much detail. This kind of lets you actually interpolate between just choosing M and just choosing D, and maybe all the fun happens when you choose some granularity in between. Okay, finally, I'll talk about the motivation. I guess this funny, simple observation here is that if you run SGD with a learning rate schedule and an adaptive preconditioner, there's this redundancy where like one scalar can kind of be exchanged between the learning rate and the preconditioner, right? So in some sense, in some view, this preconditioner, even though it's performing this update that depends on all the parameters of the network and keeps this like this auxiliary state accordingly, maybe the only important thing that it's doing is inducing some kind of implicit derived learning rate schedule. So we wanted to disentangle adaptive gradient methods from their learning rate schedules. I guess viewing this from a kind of reductionist like optimization viewpoint, this makes absolutely no sense. In general, like you can have two optimizers that converge and the grafted optimizer does not converge. So that's maybe not the point. And agnostic of how we look at this theoretically, we find in these grafting experiments that in many state-of-the-art settings, it's the optimizer that provides the magnitude that determines the convergence success and the optimization trajectory. So basically, we've kind of simplified we've performed this sort of adaptive ablation using this funky experiment of what these adaptive optimizers are actually doing, perhaps allowing us to trap what's going on in practice for better analysis. So just a little bit of these empirics. There is this conventional wisdom, folklore in practice, if you talk to people who train vision models of a certain kind, that we don't really need adaptive methods in vision, and in fact, sometimes they harm generalization performance. And we find using this grafting experiment that indeed you can rescue AdaGrad, let's say, by kind of grafting on SGD's implicit learning rate schedule in some well-tuned setup. And so this gap is partially closed by the conclusion that AdaGrad is like finding an excessively aggressively decaying learning rate schedule. And perhaps like more compellingly, there's this other observation that adaptive methods seem to be necessary for training these like GPT-3 or BERT kind of models. Certainly, like in all these empirical papers, if they're not paying too much attention to like the optimizer choice, in fact, they do tune the learning rate schedule, but they use Atom and Adagrad and such. Well, this gives us some way to actually pick apart this effect. We do this sort of tensor-shaped parameter-wise grafting of learning rates, and we find that like SGD can actually be coerced to train a transformer model successfully. And here we're plotting the kind of tensor-wise corrections that this grafting operation is performing. And indeed, this is like a new empirical finding that we don't quite need adaptive methods or adaptive learning rate schedules per parameter to train a state-of-the-art BERT model. And I guess there are kind of lots of open theoretical questions here of posing the theoretical question that that accounts for this phenomenon. Okay, that's the end of this section. I just wanted to present a few experiments and some other like very agnostic take on optimizers, where we're just going to diagnose their behavior by viewing them as generic state machines and nothing else. Any questions here? All right, great. I'll just finish up with the preview of our latest work, which is asking what is, what are the beliefs you are encoding by choosing to use a self-attention model as they do in the state-of-the-art language models and beyond? Okay, so just a quick introduction for those who have not been reading TechCrunch and got saturated on this news already. The transformer was this architecture initially proposed for neural machine translation in 2017 by some folks at Google. And the kind of interesting part of this architecture is that it's not a convolutional or recurrent architecture, at least in some immediately kind of salient sense. It uses this attention mechanism, which was like which was originally this auxiliary module on top of like recurrent networks, but only uses these attention blocks. And just to give some sense of a fun little demo, we have some access to GPT-3. I tried to get this to complete the abstract of my talk, and this kind of at least permutes ideas and knowledge around in some semi-convincing way. At some point, maybe a language model can give my talk, and yeah, this part is entirely generated. If you read it carefully, this makes no sense. Okay. Okay, now, yeah, beyond machine translation, it seems that transformers have been key to unlocking, what people are now calling natural language understanding, where you pre-train some transformer on some pretext task, some fancy fill in the blanks task on the whole internet, maybe. And then you can kind of use this as some initialization to get some good universal features for all sorts of language tasks, right? So again, just to give this some self-referential theme, this can answer basic factual questions about like certainly something that was not in the training set. And of course, like I'm very fascinated by how these architectures are being applied beyond natural language processing across, maybe most recently, AlphaCode is finally automating my high school sport programming contests. And so, there is this necessary question we must ask, maybe even before committing to any theoretical abstraction of what's going on. And I must say, like in other fields, very interesting things are going on in terms of the intersections between like the modes of analysis in kind of fields of various kinds, like tackling this problem of dissecting a transformer. This whole emerging field of Bertology is trying to reconcile the way BERT maybe is like rediscovering the primitives that like linguists like to think about in kind of in grammatical parsing. In neuroscience, I guess I've been made aware very recently of some work showing that trained on some navigation task, transformers are rediscovering place cells and grid cells. Okay, but we can ask some statistical question of like, what is the inductive bias when you are using a transformer for your as your model? So at a glance, here are our contributions in this paper. First, I guess we established some definitions, which we just hope will help people think about these things. And with these definitions, we give a name for this inductive bias for self-attention that we identify. We call this sparse variable creation. And this kind of consists of two parts. One is a classical generalization bound, just kind of derived by constructing like an appropriate cover and the appropriate norms for this architecture and some standard chaining arguments. And maybe the upshot here is that we get these sparse regression like sample complexity guarantees that only scale very mildly with the context length, where, you know, for n-gram models, or let's say t-gram models, the capacity really suffers some cursive dimensionality that like exponentiates with like the context length, right? So this is a very mild growth. And the other kind of counterpart of this is, well, okay, we know there are few functions in this class. Which functions are in this class? And we show this kind of very tedious, maybe construction of embedding a sort of like, let's say a 2 or 3 way Boolean gate with kind of constant norms in a transformer architecture. And I guess combining these two results, the sort of like upper bound and lower bound, you could say, we can start to reason about how a single transformer head is not very expressive at all. A single transformer head, of which this GPT-3 contains, you know, billions of replicas of, like a single head has a very small statistical capacity and kind of describes one sparse, like discrete interaction with the sample complexity scaling as the description length of that gate, which is just maybe like the statistical cost of specifying a constant number of pointers into the input, log t. Okay, I'll close with some fun experiments and open questions. I guess we propose this way to run large-scale experiments to kind of probe the statistical properties of small transformers. And we find that in these sorts of Boolean circuit tasks, or these Boolean gate tasks, where the task is to identify, you know, some sparse interaction of some like uniform input on the hypercube. We do corroborate this like mild scaling law of sample complexity in practice. And I must say, like these GPT-3 things may seem intimidating for, you know, someone who wants to work on theory, but really it is very easy to train a shallow transformer on CPU, and I would invite everyone to join the fun. And as for future directions, I guess we have some statistical part of this story. We are not at all done with the optimization part of the story. Like, why the heck does local search, you know, trained on you know, some internet scale corpus actually find some concise circuit that describes the training data? And, you know, that's a complete mystery that is going to keep me up for the next N years. And I guess we present one experiment just to hook everyone. If we replace this AND Boolean interaction with an XOR, right? This is a sparse parity. It can work with noise. You know, there lots of theorists are interested in this problem setting. We actually do see that transformers are, you know, spend some time like making no progress better than random guessing, and then suddenly get the right answer. So somehow this is like outside the purview of convex optimization. And you know, lots of people out there, like in the recent maybe year, are also thinking about this from some empirical perspective of identifying this empirical phenomenon where there's a sudden phase transition in training and you make all the progress like in a very short amount of time. So understanding this is something that we are super excited about. Okay, that's the end of my talk. And I guess I'm 1 minute over time, but I can take a few questions. I can stick around. Yeah, thanks for having me again.
Thank you very much for the talk. I mean, I have a quick question for this fractal optimization scheme. Do you have actually a routine implemented in PyTorch which is plug and play, or?
Yeah. Oh, I should have put this in the slides. I guess it's just like 4 lines of Python code. They're in the paper, Appendix A.
Sure. Okay. Cool. Yeah, I will try that out. And so, have you on what problem have you tried this? I mean, you said like you looked only at very simple cases.
Yeah, I think the largest thing that we tried, this is kind of very much besides the point, I guess, of the theoretical contribution of the paper, is like a ResNet 18 with like tens of millions of parameters on CFAR 10.
Okay.
And I guess the only finding here, not claiming that anything's state of the art, is that we can kind of, the learning rate schedule can poke to around like 20 times the largest stable learning rate. And that's kind of the preliminary finding here. So that like overshooting doesn't necessarily doom you, maybe is the takeaway open-endedly for experimenters, as long as you have some globally self-stabilizing schedule that amortizes your overshooting.
Got
with
it.
more overshooting.
So, okay, I have questions about also the fractal learning rate schedule. So I think like in your setup, you only consider linear regressions, right? Which I mean, which is reasonable. But I was wondering, like, have you tried like the experiment with like a loss consisting of a sum of 2 parts, where so one part is like smooth and another part is sort of like a multi-scale, like oscillatory, for example. So then yeah, this sort of like mimic the landscape in deep learning practice. And then what will happen if you apply the schedule in that setting?
Yeah, that's a good question. So actually, I guess I briefly went over this. We have like some logistic regression experiments with MNIST, and there is a little bit of L2 regularization. So exactly what like the setup you're describing is roughly what we're doing there. So yeah, I guess it's left as a mystery to us by, as of the time we completed the paper, why this works on like objectives beyond quadratic convex. We actually show some like one-dimensional counterexample, just like some log hyperbolic cosine like one-dimensional function where like it's just some silly little computational negative result where like the schedule does not get the same convergence as like would be guaranteed for like a convex function of the equivalent, like a quadratic convex function of the same like condition number. So I guess there's at least some beyond worst case analysis that's necessary here. So it's not immediately clear what the right theoretical question to ask is, such that the answer is unconditional. And that's kind of where we left off.
I had a question if that one's sort of wrapped up. I don't know soon if that one.
Yeah, sure.
Yeah. An example of something you mentioned is you had this term halfway through, and I don't know if it was learning rate. There was 2 terms, there was a C and 1 over C, and it was in the Hessian term and the schedule term, I think. And the way you presented it was, there's sort of a mathematical statement, right? You could put the C, in one place and 1 over C in the other, and of course you could have 2C here and 1 over 2C here. And I think a lot of people who try and explain why neural networks work, they say, well, see, it works because my learning rate schedule is faster, or because my Hessian's better, or my Attagrad's better, or something. And the justification for that is, see, I get some plots where I'm better here. And I think it strikes me that if people parameterize the questions they're asking in sort of a falsifiable way, like sort of a natural scientist would, where you're trying to make a causal claim that the learning rate schedule is why this is working. Presumably, then if you frame the question and try to invalidate that hypothesis, no one would have spent the last 5 years saying step size and whatnot's responsible for this. And so you come here and you say, well, note there's this mathematical thing in this particular setup, and it's very believable that something like this is buried in something more complicated we can't understand, right? But I'm wondering, I mean, it seems as if you ask the questions in a falsifiable way, you would have just avoided this problem altogether, because there wouldn't be papers saying I'm responsible for this and then I'm responsible for that. So one, what's your thought on that? And two, beyond just this particular example you have on this page, I mean, you have an example about this fractal learning rate schedule, and I could imagine you saying, well, deep learning quote works because something about that schedule. And I don't know if you're familiar with stuff Liam Hodgkinson has. He has some stuff on looking at multiplicative updates, and you get heavy tails in weights, but probably you get it in gradients or something like that. So then I could come and I could say, well, the reason it works is because we get heavy tails over here. And of course, neither of us is right, because we haven't framed the question in a falsifiable way. And I could imagine, because the learning rate schedule is coupled with the other stuff, I could imagine there's something analogous to here under the hood that we can't tease out yet. But I mean, if you could, and if we can, ask the question in a falsifiable way, we can sort of get beyond that. So either in general or in this particular example about the schedule versus the multiplicative weights, I'm wondering what your thoughts are on that.
Yeah, that's a great perspective. Thanks for bringing that up. I guess in deep learning, maybe something like my perspective on why there's so much noise and maybe why there's a reproducibility crisis here is that it's so computationally expensive to actually obtain robust experiments. I guess for these scaling law experiments for our transformers, right? It looks like some innocuous 1D plot. We're training 20,000 transformers to obtain that plot. Many transformers were harmed in the making of this, right? I guess
but
when
you could ask a falsifiable
yeah.
question without training. There's 20,000, coincidentally, but ballpark the same number. There's 20,000 publicly available models now. I mean, there was 5 years, so you could just analyze them, no training whatsoever. I mean, and you could ask a falsifiable question about those. So I think the reproducibility crisis arises because there's so many moving parts. Nothing's reproducible, and most people ask the question in a way that involves training. So, I mean, you could ask that question with or without training, right?
Yeah, so then I guess many of these claims which fail to rigorously establish some falsifiable hypothesis, like if you try to extract the hypothesis out of it, these claims do involve training, and they also involve some claim that's actually very strong and very hard to support, which is that maybe this particular heuristic or this particular rule for selecting something based on theory or measurements is better than others. I guess that's where it's extremely costly to iterate on developing meaningful beliefs in this space, because suppose you change some hyperparameter in your optimizer, which has 20 hyperparameters, then to claim that some setting is truly better than all others, you are actually making some implicit claim about the max over all other settings, and you're suffering some kind of experimental cursive dimensionality there. I sort of think that is why this kind of landscape is so crowded and full of noisy signals. People are running some coordinate descent rather than kind of local search, and the gap between these is actually some significant, creates some significant disparities in whether things are true in other settings.
The important thing about asking falsifiable claims, at least as important as the claim, is delimiting the scope of your claim, which gets to your max point, right? I mean, and theoretically, it's convenient to say it's a max over some mathematical thing, but I mean, people would have a claim that says the Earth goes around the sun because of F equals ma, which is true. I mean, up to some, within a pretty broad domain of applicability, that's a falsifiable claim, and it's been shown to be true, right? So it's not a max over everything, because that can break, but it's a max over a pretty broad thing. So I guess what I don't see in the area here, which some of the things you touched on was, make a claim not in a max over mathematic, but within a pretty broad but delimited set of transformer models or state-of-the-art transformer models that people are currently working on, right? I could apply transformers to something totally different and maybe it would break, but within the claim people are looking at. Because I think, that's the key point, that I think if you mathematize it certain ways, you're forced to have a max over something like that. But that's of course a corner case that's very different than people would be training on, or developing models on.
Right. Yeah, in light of this, I think this is why this grafting thing is a bit of an unusual paper. It's more kind of presenting some exploratory or diagnostic tool for like simplifying the experiments, and it's actually some tool I view for ablating your current setup. And like the hope is that this will help people kind of narrow down what's actually going on. So maybe this is actually a pessimistic paper in that this tool only makes sense if you are if you're kind of maximally agnostic about any beliefs out there.
Yeah.
And I guess like people
this suggests something, right? You're
this.
saying in many settings, magnitude plus direction is the same as magnitude. So what you're saying is magnitude doesn't matter. Direction doesn't matter. Get the magnitude right and iterate, or something like that, right? And that buried in there is a very plausible and could be falsifiable hypothesis that I guess wouldn't apply to everything, but I mean, within a framework of an iterative algorithm, whatever, I could see being a useful insight. Yeah.
Right, and towards this, there are some hypotheses that we falsify just in the negative results of this empirical study, where there are kind of, as I mentioned, these like various granularities of grafting, where like the most extreme version is just to extract a single learning rate schedule and just apply it to SGD, and so there is some negative result where for transformers this does not work, and so yeah, I guess. There's not a single message, I think, to be extracted out of this exploratory tool, but definitely we're very sympathetic to like these limitations and like frustrated about how hard it is to clean house in this space, and we are viewing this as some like multi-purpose broom with which to corner the dust. Also, it's good to meet you. Big fan of your work.
I like this. Was nice. Yeah. So I wish we had another hour. We could follow up, but this would be nice. But it's good to meet you and to hear this.
Yeah, happy to chat sometime. I guess I've inappropriately packed too many things into the talk.
So I have a question just to better understand it. Like if you train with your fractal scheme here, so if the step size is too large, you get like exploding gradients, right? Or the gradients will explode at some point. I mean, and you said also like you train beyond the edge of stability. Is that something you consider, you particularly analyze? I mean, do you recover from exploding gradients? I mean, quite often what I've observed, at least in practice, is like once you diverge, I mean, there's no way to come back, but magically, you diverge and then you recover, which is a bit unintuitive for me.
Yeah, that's a great question. So I guess there's a distinction to be made here, I think, between the exploding gradients problem and just like divergent training. Maybe divergent training is some simpler thing where you're like iterates just keep multiplicatively growing under some norm. And at some point, you overflow, or any number of things happen. You're in some meaningless region, right? Yeah, I guess there's like one kind of message in these preliminary experiments in the fractal paper, like would be that you can actually recover to a significant extent from making negative local progress by overshooting. As long as you kind of compensate for yourself later. It feels like some philosophical message about life.
And it kind of, I mean, you basically just show like a toy plot where you increase the learning rate. So is this like in an early stage where I explore the loss landscape, or does kind of this still happens in a late phase of training? Because I assume like if you do it somewhat like, let's say in the first 90 epochs, it might be positive, but at the very end, like if I would have a big spike, let's say like 10 epochs towards the end, it might be not that favorable.
Yeah, that's a great question. We have lots of experiments that we were kind of surprised by, but didn't put in the paper because they're way too anecdotal.
Yeah.
And one of them was that like if you apply some like warm up before you start using the fractal learning rate schedule, that actually makes training diverge, or it makes the sort of radius of kind of learning rates it will tolerate like smaller. So there's some kind of chicken and egg effect here where like we really have to reckon to understand like training stability with like training as some closed loop dynamics to even like ask the question, like what does it mean to like, what does late stage training mean if you're using an infinitesimally small learning rate, right? Yeah, that's a great question. We have not made sense of what's going on. I guess there's some related work just in pure empirics about this like edge of stability, right? Where like they find that the largest stable learning rate is this quantity that actually depends on the learning rate you're using to train the network. This is by some friends at CMU.
Is that a recent
then
paper?
it's a little tautological. Yeah, this is called like if you search like edge of stability, Jeremy Cohen is the main person on this, I think. Yeah, that's a really nice paper. I guess it came out around the same time.
Yeah, I think I recall that paper. It's called like gradient descent on neural networks typically occur at the edge of stability, right? And I think in the paper, they study the maximum eigenvalue of the loss Hessian. And I found that they just like hover like around some like value. I think it's like, 2 over stat size or something. So then I was wondering, so what happened to the, this maximum eigenvalue of the loss, training loss Hessian for the fractal schedule? How will it look like?
Yeah, we have that's on our to-do list. We have not run those experiments. That's a very, very valid question. Yeah, so I guess if I were to just say some things before just training the neural nets, I would say that if you're like, probably there'll just be some other empirical edge of stability. It will be interesting to see where it is if we kind of train at these like larger on average learning rates. Maybe like a very nice outcome would be that like training with this sort of like fuzzy schedule actually expands the radius, right? Like certainly the fact that this training kind of succeeds at all in our basic experiments, like maybe suggests that like this would happen. And then if not, then there's some new interaction of these phenomena.
Yeah, so yeah, I think another thing is, so in the fractal schedule, you show like accelerated conversion, also stability. And so I was wondering like, how about generalization? Have you like looked into that?
Yeah, that's a great question. Yeah, I'm aware of some recent work that is actually using some like negative learning rates to promote generalization as some kind of adversarial like kind of component of the optimizer. This is with Benam and some co-authors at Google. So like certainly there's some hope of kind of algorithms that are aware of stability and curvature, like modulating generalization here. I guess my view here is that like generalization is such like a multifaceted phenomenon here that it's like we're kind of far from the regime of like well, of course, uniform generalization bounds. So I think that maybe there need to be some like specifically crafted experiments to actually just like measure which features are these trained models learning. And this seems to be some wide open space that's kind of like far beyond confidence intervals, right? So I guess like when feature learning is in the equation, I don't really know what the canonical question is to even ask about generalization, except that like probably the features learned will depend on the schedule. And there's lots of work on that without the fractal learning rate. So I guess this goes back to the everything affects everything thing.
Yeah, I think because it
But
would be
this
really
may affect
neat
us positively.
Oh, sorry, sorry to cut you out.
Sorry, go ahead.
Yeah, I was just saying that it would be nice to, I don't know, to ask the right questions and try to tie like convergence, convergence stability and generalizations. You know, maybe I mean it's only like within some really like narrow setting, but it's still good to see. I mean how these three interacts with each other. Yeah, I know. I just think that yeah, it would be cool to have some result on this.
Yeah, totally agree. And I guess it's like what I've been trying to convince people, for better or worse, just in kind of personal conversations, is that it is meaningful to think theoretically about these deep learning pipelines, and like there's a very, very real possibility of moving the needle on like how things actually work, how well things actually work, just by kind of fundamental theoretical research. Yeah, I guess like just towards this, like the sort of bitter lesson I've learned is just not to commit to any particular worldview.
And also like because so here the fractal schedules apply at the level of gradient descent, right? So have you thought about like doing something similar but at the level of the architectures? So you can think of like deep level as some type of like dynamical system, like you know, have many layers. So each layer is like you iterate once and so on, right? And then so it's sort of like if you write down the equation, it looks like the gradient descent equations, except that you don't have you know, you don't use gradients to do this, but it's just very generate like neural network mappings in the equation, right? Something like this. So then maybe you can do similar things. So like, so you maybe you so you can think of it as some kind of discrete dynamical system, and then with some time step. And then this time set is sort of like a learning rate in the gradient descent context. And now we want to find a schedule for this time step that depends on the layer.
Yeah, so I guess in the asymptotic limit, the best optimizer is the one that just writes down all of the weights you want in a hard-coded manner. Or you know, the best way to train an RNN is to write down the Turing machine that gets you the right answer. So I guess like there's some sense in which like this is actually some RL problem where like these different training environments are environments. You must pick your kind of policy class to react to in the face of like interaction with the environment, which is just getting feedback that depends on your own decisions from the kind of stateful optimization problem. Like in some sense, like there are all the horrible considerations of RL here with a sort of really high dimensional state space. Like really like learning is this dynamical system here, and like to like there's some okay, all of these jokes are just towards pointing out that there is some peril of overfitting your policy to any particular setting. So maybe the pessimistic answer maybe here is that like there's no single right thing to do. The optimistic thing would be that there are many things to do research on.
For sure, yeah, that agree.
Yeah, I guess the message of this talk really is it's as bad as it seems, but some slices are not as bad as they seem.
Yeah, yeah, yeah. I mean, of course, sure. I mean, there are many like interesting questions, like I mean, in different contexts, different settings, and I mean, it also depends on just too many like variables, right, to take into account. So there's no really like one, unified way to tie everything.
Yeah, it seems better that way. I think maybe there should not be a unified approach to statistics or analyzing data under uncertainty. So probably the best we can do is to have some like toolbox and understand it.
Yeah. Oh, by the way, so it just happened that I am I think a collaborator. So we were looking at so sort of like not really learning rate schedule, but also like learning rate plus some noise, and then we want to tie these to generalization. So I think we were looking at your paper at one point. So then so maybe I will go back to I will come back to you if I have any questions on that. Is that fine?
Yeah, sure. Of course. I feel like I always learn from these kinds of interactions, so it's very happy and grateful that people are following up and trying to run the experiments that we did not run.
Okay. No, like we didn't try to do like similar thing. It's different context, but somehow like I mean there's some inspirations that that you guys provide, and yeah, it's a different framework that we are going to use. But I think we can talk about this later. If I have like more questions about the fractal schedule later.
Yeah, sounds good. Please feel free to reach out. Yeah.
I think we should wrap up because probably the Zoom meeting will terminate in 1 minute. So yeah, thank you very much again for the talk. And let's
thanks
talk
so much.
More offline.
Yeah, this was a lot of fun.
Yeah, thank you.
All right, see you.
Okay, bye-bye.
Bye.
Bye.